That's it. So without further ado, a man who, how do I put this, has never told me how to get people on the moon, has advised me on how to shove things up Uranus. I don't know. That's a science joke. It really is. Mr. Theo Schlossnagle, our mad scientist leader.
Yeah, lovely. Thank you. I suppose I'll think of a creative way of telling Robert where to stick it later. But so thank you all so much for coming to Surge. I assembled this. So the lightning talks were awesome for me. Actually, one of them resonated more than the other as I was sitting over in the corner and and the person got up and said, when you have a lot of kids, all of those improbable things always happen, right? So are one of my children sick? Yes. Is my wife sick? Yes. Did they get me sick? Yes. I mean, that's the always state of that. So it was hard. I was kind of living in a cloud for the last 2 days. So I didn't prepare anything. And as all good speakers do, I prepared all of this in the last hour, reflecting on my experience of Surge that did not involve nasal congestion. So Gene fucking Kranz, right? That was awesome. That was my highlight. That was great. Absolutely fantastic. There were some really interesting tweets that happened during the conference. One was, if you insist on calling C a high-level language, you're implying we need some stronger adjectives for higher-level language, making Ruby heavenly. That was said by no one at Surge. So Ruby is an misinterpreted language, right? And this is how that works. But what was said at Surge, understand the default behavior before you mess with code. I had never heard this before phrased as advice, right? How often do you warn someone first? One of my favorite movies is Real Genius, and there was a statement in there that was very clear. Damn it, don't touch other people's things. So it seems much more constructive to take Rachel's advice and actually observe what code does. So I thought that that was really useful. And 2 years ago, in a city far, far away where The Wire was filmed, I shared an epic tale of woe and suffering about debugging systems. And it was really an effort to provide self-gratifying therapy so that I could sleep better. And this year, in the land of relentless taxpayer money spending, I suffered a production outage over the last couple of days, again related to OpenSSL, but this time in Apache traffic server. So we have this issue where certain requests to the machine, they're sending partial documents over SSL, and then they pause, and then they time out after 30 seconds, which of course makes our users supremely happy. But there is a rule. There is a rule that if you are a victim of abuse and you are receiving therapy, that the hostage situation should really be over. And we haven't fixed this bug, so I don't really want to dive into it. Suffice it to say, every time I go and try to find where the bug is, and I'm like, who fucking wrote this? And I write and get blame, my name is on the code. So at least only I look like a dick. Alternatively, I would kind of look back at this conference in the non-production troubleshooting sense and look at what happened and what people thought and what people shared with me. And somebody asked me what I thought of this conference. They're like, so what do you think of the conference? And it was like Gene fucking Kranz, right? That's it, right? Now, there's more than that. Someone asked me, they said, a lot of people here really optimize the hell out of their stuff. I mean, they're talking about CPU instructions and cycles, and how do I get more packets over my 10 gig links, and how do I not, how do I make sure every interrupt that happens for a reason, sort of thing. And they're like, I feel like I'm over-optimizing systems if I do that. And then later on, maybe I'm screwed because I didn't. So like, how do you know? How am I right? And there's a really unsatisfying answer to that. But first, I will misquote someone. We should forget about the small inefficiencies. Efficiencies, say about 97% of the time. Premature optimization is the root of all evil. It's a misquote because he didn't stop there. There was a period, but there was another sentence that immediately followed that one that says, yet we should not pass up the opportunities of the critical 3%. This conference is about people sharing that 3%, right? Because we all got screwed, things fell apart, and most of the time we chose not to optimize when we should have. So while I don't really have an answer to this, when you see it, you know it. It doesn't take a good actor to recognize a bad one, right? So correctly identifying what is premature is really what separates the master craftsman from the apprentice. So when you see someone who doesn't chronically make those mistakes, those are the people that you look to and you listen to. And we try to make sure that those people end up speaking here. So that's kind of the goal. I don't know how I got here, but I'm a fuck up. So Cantrell said earlier, on the topic of retaining superlative engineering talent, he kind of made a claim, and I thought it was really interesting. He talked about the CAP theorem. It's kind of funny. He was like, everybody understands CAP, choose any two, but oh, by the way, P is required. Kind of changes the dynamics of that, right? So you don't actually get to choose C and A, right? That doesn't make actually any sense in systems how they're implemented. But he related that to quality, schedule, functionality, right? The triangle of power in project management, like cheap, fast, or good, choose any two. And what he said was, if you don't choose quality, all of your good engineers are going to fucking quit. Which is really an interesting idea, and it made me think, God, you're really wrong. And you're wrong in context. The context was that when you're building a project, when you're building a deliverable and you're trying to deliver something on a schedule, you really do need to have quality because good engineers aren't interested in building shit. We want to build beautiful things. We want to build things that are work, that correct. Good engineers also understand tolerances and compromises. That is not an affliction of quality. So you really do need to choose either schedule or functionality, right? But that's for engineering products, and not all of us are always engineering products. When we're doing operations and we're doing debugging, there's one thing that can never change, and that's the schedule. And that was what Gene reminded all of us of. We have a problem, and in 2 minutes, if you don't fix it, everyone's dead. Right? We don't have that exact problem, thank you, which is wonderful. But we're still losing money. So all of the things that we do in operations and that we do in debugging, when it's related to operations, critical outage debugging, is all time-bound. So you do actually have two choices, but S is not on the table, which is a really interesting problem, right? And creativity comes through constraint. But what that reminded me of is that in the world of operations, so understanding how our systems work is a fundamental necessity of what we do. And while I was in awe and inspired of Mr. Kranz's speech, I felt depressed. Because I don't feel like I understand any of the systems that I run as well as the most basic engineer on his flight control team. When he talked about tools, see if I have that. So when he talked about tools, all of those engineers, all those computers, all those people, it's not that they could just do math. It's that they solved problems with math, right? Most of us do not understand how our systems work. I have a lot of anecdotes. I have most of the most funny anecdotes of being a consultant are realizing people can't multiply. It's amazing, because when you scale and you're like, I need to make my site 100 times faster, everybody ends up multiplying everything by 100, right? It's all a multiplication exercise. And when you're not using your machine, but you think you are, you multiply by 100 for no reason, which is really neat. So we have to strive for a better understanding. And Gene fucking Kranz, right? So he made me realize that this is a tool that, how many people here actually can use a slide rule? If I tossed one out and do math right now, there are maybe 8 hands. I was really sad because my father taught me how to use a slide rule. I know I would need at least a 1-minute refresher on, dude, I can do all the logarithms, everything's fine there, but like, it slides. Oh yeah, okay, right now I got it. Remember this is a tool, and I always say, like, it's a great engineering question when I ask somebody, do you know how to use a slide rule? And it's not because I want to know if they know how to use a slide rule, right? Because using a slide rule is the same question as asking, can you use this tool? Right? Can you use Mathematica? Do you know how to type an equation into Mathematica? Right? That's a tool. This is the chronic tool. This is a tool virus that we have in our industry. This is a different type of tool. This is not what I'm talking about. I'm sure that some jackass somewhere in the 1970s or 60s was like this too, but I hope he was beaten. This is prevalent where we are. Not in our company, thank God. In our industry, it's prevalent. So then versus now, the question is, where have all the good engineers gone? And to me, that's a really disturbing question, right? This is a conference of about 400 people. And I would attest that we are the elite. I mean, it's not that there is no engineers better than us, but we are in the upper echelons. We are the people that are choosing to go to a conference for career enrichment on problems that are hard, that are germane to our industry, right? We're coming here to share with others and learn. That's what good engineers do. And yet, we're posed with problems that I think are really remedial that we can't solve. So this is a common problem that I hear from people, but I don't hear any answers. So we give people products, and they say, don't tell me what it was designed to do. Tell me what it can do. Right? And that was the flight, you know, when the oxygen broke, and they said, I don't care what anything in that spacecraft is supposed to do. Here's the duct tape and the design documents. Go fucking figure it out. We're not going to lose anybody. Right? That's an interesting question to ask somebody. Those are not the types of questions we get asked. And when I hear questions to people, I don't hear the answers that I want to hear. There was a really interesting little conversation. It was more of a monologue on Twitter about a review of Cassandra. There was a big argument on whether or not vector clocks were a good idea or a bad idea, and Cassandra doesn't use them. They use timestamps. And is that correct? I'm like, does anybody know what software correctness is? It means that it acts like it's documented. So if it's documented to be stupid and it works stupid, it's correct, right? I mean, that's not really the question that you're trying to answer, right? What you're trying to answer is, does it fit the problem at hand? Does it service me? Is this a useful database? And of course, the answer is yes. There are plenty of people that use Cassandra. But the problem is that people couldn't quantify that answer very well. So great, I have timestamps that actually end up reconciling things. OK. I have a certain amount of latency between my machines. I have an average arrival rate of, say, 1 request a second. What is the likelihood of me having a time-based collision in a single day? Almost every answer I hear from everyone is, that's unlikely. Like, that's not a fucking number. Like, that's not useful, right? I mean, can you imagine? It's like, we have 12 seconds of burn left. Like, can we hit the Earth? Maybe. I mean, like, it doesn't really make sense, right? You can't make educated, intelligent decisions without being able to quantify why. So, in a little bit of digression, I show these things to people all the time, and most people in our industry don't know what they're looking at. They don't see this. So what's the first one? The first one in the upper left. Anybody can guess what the first is? Normal distribution, I heard it. The one next to it? What's that? The Poisson is somewhere else. I have a Poisson going for the upper right. It's not the upper right. It's the lower left is a Poisson distribution, which describes the probability of arrival rates. Anybody have web servers that serve traffic where clients arrive at a certain rate? That's the probability distribution of them arriving at a certain rate. That is your web server's probability distribution. If you deviate from that, you have an anomaly, right? So understanding what that looks like is pretty important. That is the foundation. You'd use the cumulative density function of that to be able to figure out what's the likelihood of having a time-based collision in Cassandra. Honestly, I was sad because I thought about this and worked it out, and I was like, it would take me at least an hour to answer that question. And that's what I do for a living. I mean, that's kind of my job, is distributed systems analysis, right? I felt like I needed to go get smacked with a slide rule. And I think that the problem's changing too, and I'll get to that. The one on the lower right, anybody know what that is? Big G. gamma distribution. And the one on the upper right is a student t distribution. So maybe you get it. Maybe you're like, yeah, so maybe I should learn a little bit more math. Maybe I should understand why all of those things are. And the reason that I'm saying this is because I hope that everybody understands this, because this shit is about to get real. Like, it used to be that we would plan these things out and not be able to observe them because we didn't have the systems to collect that data. But now, every single database request you do, 1 million a second, you can measure the latency on every one of them and the dispersion rate, the interdispersion of arrival rates. You can measure all of that. And you can record it, and you can visualize it. You can jam it in R. You can jam it in Mathematica. So the ability to use a slide rule and use Mathematica is not really relevant. It's being able to ask the right questions because you understand what you're looking at. And that, I think, we're starting to lose. Certainly in the education system. I have to go into engineering fields to get that, right, and not computer science. I think computer science needs that. Another thing that Cantrell said on the topic of quantitative metrics or measurement was really interesting, was he said, you have to know when to quantitatively measure things and when not. For example, don't quantitatively measure human beings that work with you. I don't know, it's kind of dehumanizing, I think. I think that we are naturally quantitative beings as engineers, so you can't help but do that a little bit, but you want to limit it, right? But quantitatively measuring all of the systems that you operate is something that's happening. If you're not doing it today, you'll be doing it tomorrow because all of your competitors are doing it. And now you have trillions of data points flowing at you, and if you can't ask the right questions of those, I think that you're going to be poor off, right? You're going to be in a bad place when you can't ask those questions. So what we have is a big data problem, right? And I don't know, the definition of big data seems stupid to me for a really long time until I thought about it in a different way. Big data, it's really, really obvious when it happens to be personal. Like, it's too much data for me. Like, great, I have Hadoop. I don't know what question to ask. I don't know what algorithm. I don't know what distribution this is supposed to model. I don't know what the fuck to do with my data, right? And there are a whole bunch of companies out there that selling me things that can do stuff with my data, but they're not telling me what. And I feel like if we went back to 1970 and took, I don't know, 10 of those mission control people out and gave them 1 month of training on what the hell a computer was and an internet system and arrival rates, and I said, oh my God, we're going to have a 15% increase in traffic. What's the likelihood of collisions? 35 seconds later, they're like, oh, that's jumping to 6.2% with an error margin. And I don't think I'm wrong. I think that they could do that because they understood how systems work. Most of them were physicists, right? I mean, you understand physical systems and how they work. And we actually deal with a ton of physical systems. As all of our systems are distributed, I mean, Archer said it, I mean, latency is the mind killer. More than anything is because it actually drops into a real equation that affects real things that you can model, right? So there is a real world that every bit you push now interacts with. It's not magical. So another thing that, like previous examples of this in the past were, I think, a lot simpler. We once had a client that had a search system, and they were searching leucine indexes. And the leucine indexes were about, I'll anonymize this. They say they were about 100 gigs. And they had about 64 gigs of RAM in the box. And they had these 10 boxes. And okay, so like 100 gigs of disk space on a box per index. You've got 64 gigs, so clearly it doesn't fit in memory. Let's say we have 4 gigs dedicated to the OS. So I have 60 gigs of space in memory that I've got my leucine indexes in. So I'm 40 gigs that won't fit. And they're like, okay, and we're beating the hell out of these things. They're doing 4,000 disk IOPS a second. Okay, so now you actually have to think, how do computers work? Which too often is not the question people ask themselves. They go, oh, 4,000 disk IOPS, what kind of disks do I have? Like, how many more disks do I need to buy? That was what they said. Like, we need to buy more disks. We need to buy more machines. So over 10 machines, we end up having 40,000 disk IOPS. So, OK, we need to buy 10 more machines. And my first question was, what the fuck are you searching? That you have 60% of your index in memory. This is all random indexes, and they're small return sets. Are they full return sets? That was my first question. Are they full return sets? No, they're not full return sets. You're searching for items, and you're getting like maybe 10 or 20 back at a time. It's pretty random. Like, so you're doing random searches. 60% of it fits in memory, and you're doing 4,000 random disk IOPS a second to satisfy that. Like, how do you keep that magical 40 gigs hot, so hot that you have to go back to disk for it? Right? Because as soon as it gets hot, it comes into memory and something else falls out. But then I need to go get that 4,000 times a second? That just seems really unlikely unless you're reading all of the data all the time. And they're like, I don't know. OK, great. We can all agree. Let's figure that out. Like, what's the problem there? And we're troubleshooting this, and we're looking at it, and we log into the box, and I'm looking at it, and I'm running IOStat, right? And the first thing you log, Unix people, the first thing you do when you log into a box, you run like mpstat, you run IOStat, you run vmstat, figure out whether or not your Titanic is already sinking, because otherwise you need to evacuate, right? You don't fix any problems. So I'm running it, and I'm like, IOStat's returning 0. There's zero requests. And I'm like, IOStat doesn't see the disks you're using. Like, what disks are you using? Because, I mean, that happens. You're like, IOStat. It's like SD, I don't know, what OS you're running, SD0 through SD10. And it's like, oh, no, we're using SD40 through SD50. It didn't fit on the screen. Well, I'm looking at it. They're like, no. There's only 4 disks in that box. Well, how are you doing 4,000 IOPS a second? We're like, well, we have this cacti graph that shows it. It's 4,000 IOPS a second. And we're looking at it. And anybody know what M means? It means milli. So it's 4,000 milli IOPS a second, which isn't the same, actually. So, and instead of buying 10 more machines, the true answer is that they could probably drop to about 2 from 10. They left it at 10, said we'll get bigger. But it's not really the point. The point of it was that when you framed a problem to an engineer, the first thing that you have to do is rationalize the conditions you're given. Like, am I still operating on planet Earth under the physical constraints I realize? Like, E equals MC squared. Do those values mean the same thing still? Right? Those are great things. I was on a phone call with a database vendor who shall remain nameless. And the client was saying, we need a sequential counter that upgrades, just a sequential counter. I want to get 1, I want to get 2, I want to get 3, I want to get 4. We need to pull about 500 of these a second, and I need coast-to-coast redundancy. And I want them to be active-active. And the vendor was like, well, we can do that. And I was like, mute. All right, there's a problem. All right, so then we're unmuting, and then I was like, yeah, that's interesting. I mean, how do you do that? You grab 10 at a time. That's usually the case, right? I'll grab 10 at a time, and I'll assign from those 10, and if I fail, I'll do fallover. So they increase, but I can get them out of order and things like that. Or I do groupings of those. There's a lot of different ways to cheat and still get close to the right answer. And they're like, no. No, you go to the data center. It doesn't matter which data center you go to, and you always get the next number. And you can do 5,000 of those a second. And I'm like, and at some point they were being really obnoxious, and I was like, I just have a really question. How fast do we need the speed of light to be on your database system for it to work, right? This doesn't make any sense. Like, there are certain numbers. I can send a packet from the East Coast to the West Coast to the United States only so fast in a vacuum, and it still doesn't work for you. Like, this doesn't make sense. So as engineers, I think we need a much better understanding of our systems, because not so much in software engineering and developing those systems, because we have time, we have patience, we have large teams, we have great communities. But when shit goes wrong, and we're out there and nobody's dying, hopefully, in any of your environments, they're not in ours, but people are losing money, you're looking bad, you need to get the systems up. People are relying on you. Your systems stay down. You know what's obviously not as bad as losing a life? Losing someone's livelihood, right? if I'm a cloud provider and my cloud goes down for a whole day during a conference, for example, I don't know, companies that don't engineer their systems very well can go out of business and people lose their jobs. Like, this is shitty. I mean, this is a real thing. When you keep your systems reliable and you power people, you empower them to have a fruitful life, right? It may seem like a stretch, but the things that we do actually improve the quality of other people's lives. So it's really important that we be able to fix them quickly, and to do that, we all need to have a much better understanding of what the hell is going on our systems. And this is a big challenge because we run a lot of systems. I know I see some familiar faces in the audience where I know what their architectures look like, but we did a survey like 2 years ago of our clients at OmniTI. And let's see if I can remember the numbers off the top of my head. The average customer had about 6 million consumers that use their site. They had 50 different repos in Git or Mercurial. Almost everybody used Git. They contributed back to I think 2 projects a month, but up to 50 patches a month to open source projects that they didn't run. They had I think an average team of about 50 people working on their sites. The interesting part is that they had 3 different database technologies, 3 different networking vendors, and they had 6 different programming languages. I think it was 6. And you're thinking, well, that is stupid. I think maybe 3 years ago I would say that's a stretch. But now, I mean, like, you've got C. Everybody's got C. If you own a large architecture, you have to fix your own bugs. If you have been wronged badly in this life for infractions of a prior life, you also are dealing with C++, as I was today with ATS. Horrible. You're likely dealing with Ruby, because somebody said, I need some configuration management in your configuration management, and they all seem to be written in Ruby. You're dealing with probably JavaScript if you're running a website. You may even be dealing with it on the server side. And then you've got your variety of scripting languages. You've got Bash. You've got awk to make somebody happy somewhere. There's still no ass kissing in this conference, though. Certainly not mine, but Brian couldn't deliver. And you've got other languages as well. I mean, in our stack, we've got Java and Lua and Perl and JavaScript and C and C++ and a whole bunch of different things, right? I mean, and like that's like an entire stack. When a user loads in Circonis, for example, when a user loads a graph, you hit every single one of those languages. So when something doesn't load, it's not going to be in all of them, but I don't know where it's going to be, and I need to understand the entire stack of the system and be able to understand how things work. Like, how do computers work is the first question you ask. And when you answer that question pretty well, being able to narrow down on that target and hit the target turns from a 6-hour exercise involving a team of 20 people into a 2-minute exercise involving you, right? And that's really, really important. Something we encourage all of our engineers to do, but still, it's a huge challenge. So I think I don't actually have the answer to that, which was what I was thinking about for the last 2 hours, is how do you teach everybody math? I would love it if everybody on my staff could whip out an HP calculator or a slide rule or Mathematica and answer a question like, what is the likelihood, how fast will a vector clock grow if I do, inserts at an average rate of 30 a second with conflict resolution on React, right? So if I'm doing certain things on React, like, model that for me. Like, I don't think that's, I mean, how many people here in the audience think that they could model that? Probably like 3 hands. There's a couple. I'd expect 5 hands in the audience. I think that in order to go forward as our systems become much more complicated, that number is going to have to turn into like 20%. And I don't know how to get there. And that's a really big problem. And I'd love people's ideas on that. Feel free to do it offline, because otherwise talking about education in a public forum is never a good idea. But I mean, I think it's a really, really significant problem in our industry. And I don't see our new candidates coming in looking like that as well. I mean, we've hit, and at OmniTI, we've had one new candidate in the last 2 years that could probably answer that in a half an hour with some Googling. But it's actually a hard problem. So the other ones are easy, though. I think the other ones are really easy because everybody knows how fast a disk spins, right? Everybody can read the specifications on an SSD. And this is what benchmarks are great for, right? Benchmarks may be lies, but they're never low, right? So the SSD that you buy, and it's like, we can do 180 megs a second random I/O at any block size. It's like, no, you can't. But I know you can't do better than that. So I can bound everything that you've promised, right? So it's really not designed as a scaling exercise. It's designed as a are you smoking crack exercise. So when you have a database system modeled or queue modeled, and it says, oh, I can request response queue, and I can do 4 million a second, and it's like, are the computers touching with the same atoms, right? You can't go back and forth that fast, right? So incorporating physics, incorporating all of the benchmarks that we have from our software, I personally find benchmarks as a great, while they're an upper bound, they provide an awesome lower bound to the size of the system that I'll have to build. So if all the benchmarks are perfect, my system could never be smaller than this. It could never be faster than this. It could never do more than this thing. So when someone says, I can do that, it's like, you don't understand your problem, which is fine. We can clarify. We can work through that. But we're not talking about the same things because I live in the real world. So that's all I've got. I've enjoyed Surge, and I've hoped you too. So tell all of your friends, and be here next year.